school way of how they used to teach charge distribution. Owen, you might never be the same after you see that, so,
After I see it's fall slowly.
huh?
It was weird, but
It's not that weird.
it doesn't seem real. I just haven't accepted it as reality yet.
It's just magic.
Yeah.
What do you mean? What?
Charles, can you beat Cohen over the head with a flag?
I'm trying to drop I just take it from here. Are you okay? How much forest do you think would be taken? There's not enough.
Cohen, stop,
And
seriously.
Well,
That's annoying.
oh yeah, it does. Yeah.
It's just got a little charge on it.
Yeah, no, not like that.
Yeah, it is this one.
Oh, just keep it there for.
Or with it.
Yeah, it's really. That looks like a video game. It's like bullet time.
Yeah, and well, I don't know.
Okay, so this is kind of the old school schematic of charge distribution. So you have three metal spheres, just like instead of having two, we're actually gonna have three. So initially you're told that sphere A has no charge, it's just neutral. B, whatever the charge is, it's just Q over 2. Okay, it could be 10 nanocoulombs, it doesn't make any difference, it's just Q over 2. And C is a full negative value of the charge. Okay? So this is your initial set of conditions. They're each separated out, so they cannot be near each other, they're separated out. So then, what we're going to do is we're going to touch A to B. So we're going to take those two spheres and we're going to touch them to each other. So let's start with C. What's going to happen to C?
Nothing.
Absolutely nothing. Okay, it's not part of the story. C is going to end up here at negative Q. When A touches B, what's going to happen to the charge on B? You just have to assume that it's, unless you're told differently, you just have to assume that it's even. So what's half of Q over 2?
Q over 4.
Q over 4. So here's how you can always check that you got this right. If I take negative Q and add that to the initial Q over 2, what does that add up to?
Negative Q over 2.
Negative Q over 2. So what that means is at any point along the way, if charge is going to be conserved, which it is, everything when you get done has to add up to negative Q over 2. So no matter what I do, when I get done, everything still has to add up to that same value. Now, at this point, then I'm going to take sphere B and touch that to C. Now what's going to happen? What's going to happen to the charge on A?
Nothing.
Nothing. That's still going to be Q over 4. So now, how can I find the charge distribution between Q over 4 and negative Q? Or add them together and divide by 2. So if I take negative Q and add that to Q over 4, what do you get?
Good question.
Negative 3Q over 4.
Negative 3Q over 4. Everybody cool with this? Then what?
Divide that by
Then I can divide that by 2, which becomes what? Negative 3Q over 8. And this is going to be...
Negative 1.
Now, how can you check that this answer is right? Add them all together, see if it adds up to...
Negative Q over 2.
If it does,
We do.
You odds are you did it right. If it doesn't, you know that it's a train wreck. So this was the old style conceptual way of going, hey, do you understand that charge has to be conserved? And the whole key to this is that the spheres actually touch. And these are conducting spheres, so those values can spread out evenly. Unless you're told differently, and some problems you are, but unless you're told differently, you just make the simple assumption that the charge splits between the two of them because that's the easiest thing for Mother Nature to do. Okay, now we'll spend some more time talking about this force equation.
It's weird gravity.
Well, kind of. So, your book uses a weird value for K. They actually use like 8.99 times 10 to the 9th newtons meters squared over coulomb squared. Your equation sheet on the AP side they use something even weirder, which works out to be 9 times 10 to the 9th. They use, where is it? Hold on.
I'm sorry.
And I'll explain what this means in just a second.
It means that electricity
Oh, yeah.
lies.
One over
The
4
same
5
law.
Epsilon naught.
Oh.
Wait, do it at the angle.
I don't know.
Do that now.
I'll explain it in just
But
a
it's the
second.
same.
It's a weird thing.
Oh, it's a different constant. Oh, is it?
If you shake
So
it
it's
right
not
now, it might not go down.
Oh, the.
But so it's the same units, but a different constant, but it's the same constant.
Yeah.
What is vacuum?
Okay. So if you look on your equation sheets, what you have for this lowercase k, this constant, the pure mathematical version of this is 1 over 4 pi epsilon naught. You have what's called the vacuum permittivity constant, and then you have the vacuum permeability constant. Though both of those are more mathematical construct, they came out of Maxwell's equations. James Clerk Maxwell, he was the first one to kind of quantify and mathematically describe the motions and how electric fields and magnetic fields interact. He actually mathematically predicted the speed of light before we actually measured the speed of light. So if you're ever in Edinburgh, Scotland, and he was the famous Scottish guy, they actually have a big statue of James Clerk Maxwell in downtown Edinburgh because that was like their claim to fame. Kilts and James Clerk Maxwell, that's Scotland's kind of famous thing. So your book technically gives a more precise value of 8.99. Realistically, everybody just uses 9.0 times 10 to the 9th. If you want to store that in your calculator, that would be handy. And again, you end up with these same units because the vacuum permittivity constant is coulomb squared over Newton meter squared. But then when you plug that in and you multiply that by 4 pi, and then you flip that over, that's where you get the 9.0 times 10 to the 9. If you're a hardcore mathematical person, okay, and it's like, oh, I was related to James Clerk Maxwell, oh, I'm going to use the 1 over 4 pi naught. Cool, okay, you can do that, okay? Everybody else just in the universe just uses 9 times 10 to the 9. This is the more pure, correct way.
No.
Realistically, everybody uses 9.0 times 10 to the 9. Okay, it's a number. Just go with it. So, here's the deal. What's the odd thing about this, as Andrew kind of alluded to, is that it's kind of weird gravity. Because the unique thing about this is that you could have 2 positive values. So if you have 2 positive values, what's going to be the sign of the force?
It's gonna be
Positive.
negative.
Because you have two positive charges, so what's that gonna try and do? Repel or attract?
Repel.
That's gonna try and repel. So you could end up with a positive force. If you had two negative values, that's also going to repel. But if you have a positive and a negative, then you're going to attract, okay?
Let's
So
go
you don't have to worry about that gravity. Gravity is just F equals big G M1 M2 over D squared. Cool, okay? You only have to worry about that being an attractive force. With this equation, the math is kind of the same, but you just have to worry about, hey, is this gonna make these particles attract or is it gonna make them repel? That just requires a little bit more of an added thought. So, simple calculation.
You didn't do anything, Danny. You're okay. I was asleep.
Okay? So, you have two charged particles, 10 nanocoulombs, they're separated by a distance of 2 centimeters. I want to calculate the force that exists between these two, okay? So, first off, and this is why you kind of have to look at electric fields as well. What force are they going to feel? An attractive force or a repulsive force?
Repulsive.
Okay? So this is going to try and push both of these in this direction. Later on, once we actually begin to study the direction of electric fields, because electric fields are defined by the direction that a positive charge is going to move. So if you put a positive charge right there close to that 10 nanocoulomb, don't worry about the other one, don't worry about this one. But what's that 10 nano, if you put a positive charge near that positive charge, what's it gonna feel? Repulsion or attraction? Repulsion, because those are positive charges. So the direction of the electric field from each of these is going outward. So basically what happens in the middle is that you have these electric field lines, it's like a battle. So they're both coming out, they're running into each other, they don't like each other because of the fact they're both going in the same direction. So that repulsion, actually caused by photons, which gets even weirder, is what causes that feel and to go, oh, I don't like you because we're the same, and the interaction of those field lines repels like this, and that's why these are going to try and get forced apart. So if you were to actually want to calculate the value of that force, so you got 9.0 times 10 to the 9th newtons meters squared over coulombs squared. Now, you have 10 nanocoulombs. So nanocoulombs, nano is probably, especially when you deal with electricity, is probably the most common prefix. So nano means what? 10 to the what? Negative 9. So you have 10 nanocoulombs. So you could just write that as 10 times negative 9th times 10 times 10 to the negative 9th. And then you've got the 2 centimeters, which is how many meters? 0.02, and that's going to get squared. Now, conveniently, and this is why nanocoulombs is used a lot, because you have 10 to the 9th times 10 to the negative 9th. So right away, what's going to happen to that exponent?
They cancel.
Yeah, so that first exponent just cancels out. That's why you use nanocoulombs a lot with electricity and charges, because 10 to the negative 9th will cancel out one of the other 10 to the 9th, which is more important, especially if you were doing old school slide rule stuff and you had to do these calculations by hand. I was talking with one of my former students, I don't remember, and they were in the college physics class, and they were forbidden from using calculators on the test. I don't remember who that was. Yeah, couldn't use calculators on the test.
What college?
I don't remember.
Oh, that's crucial.
It wasn't K-State or KU, let's put it
Was
that
it
way.
WSU?
No.
Okay.
Yeah, then you're good?
We're fine.
Okay. Anyway, so here's what you're gonna do wrong, okay? You're gonna get all excited,
use calculators on this.
and then you're gonna forget the square of that bottom number.
Uh-oh.
Okay?
Yeah, probably. You wanna do that, Mr.
Bird, I would
why?
never.
You've already done it.
Anyway, so what do you get? Somebody run the numbers. What do you get?
7, 20.
No, you don't.
7, the most random number.
I don't know. What do you get?
2.25.
What'd you get?
2.25 times 10 to the
No, it's 7.
2.25 times 10 to the negative.
Supposedly 7.
Oh, I was going
Okay.
Odd, and it's not 5.
Now, what if,
I'm gonna check that.
what
It's
if
not 1 or 9.
Okay.
one of those had been 25 nanocoulombs? Okay?
Oh, I see what you're saying. Never
Hold on,
mind, that's not right.
it's 2.25 e to the negative 30.
Did you forget to square it?
No, I squared it. I did meters, not centimeters.
He didn't convert it to centimeters.
2.5 e negative 13.
So is it 2?
Owen,
Is 2.25 times 10 to the what?
Negative 30.
Negative 30.
watch somebody have forgot to square it though.
Wait a second.
All right, guys.
Oh, I forgot to multiply. No, that's my bad.
You imbeciles.
Look at the order of magnitude.
I
10
got-
to the
no,
negative
I
9
got-
times 10 to the 9th.
I got Jake's answer. I forgot to multiply by the 9 times some of the 9.
What
I got
imbecile?
Jake's answer.
That wasn't on my bingo card. Of course, don't forget to multiply by K. That wasn't on there.
But it should be.
I know.
You should have forget to
Now-
multiply by everything on that.
How
What,
big's the
so,
board?
anyone but Cohen with a calculator, redo that calculation and make it 25 times 10 to the negative 9.
Cohen,
Keep
your
one at 10,
calculator principles
change the other one to
privileges
25.
have been revoked.
What do you get?
5.625 times 10 to the negative third.
Bigger value,
Did
right?
anybody else get that?
Why is it bigger?
Yeah.
Good.
Because one has a stronger charge, so it's
One
gonna
has a bigger charge, right? So the force is
be
going to
more
be bigger.
repulse.
Which one of these, the 10 nanocoulomb or the 25 nanocoulomb, feels the bigger repulsive force? The 10, the 25,
They feel the same.
or do they both feel the same?
They feel the same.
It's the gravity.
Oh, why do they both feel the same repulsive force?
Because it's weird gravity.
Newton's third law, right?
No.
Yeah, one can't feel more than the other one does, right?
It's weird gravity.
Okay,
Why do you put your thumb?
so let's go back to the 10. So at this point, these are going to start to repel each other, right? If you knew the value of the force, which you do, and if you knew the mass of the objects, what could you calculate?
Acceleration.
The acceleration. Right?
Wait, it's
Oh, yeah.
Let's go. We're back to something that's familiar.
Two like positively charged particles at each other, and you have to calculate like how they bounce back from
That's
each
2
other.
equations, bro.
Yeah, and now we know acceleration.
No, it's
Yeah,
not
that's
how they
all together.
bounce, it's how
I
they...
won't do a bounce.
You should, that would actually be very interesting.
Shut up.
It's subtle gravity.
No.
It's that the
So
gravity
you
is
said it only has to be
negative.
2. What if he has them in a
I
triangle?
like my grade.
It's literally just acceleration in the opposite direction from gravity. It's not that complicated.
Why?
It gets worse if if you have to do it in more than 1 or 2 dimensions.
Circuits are
Get that
easy.
one.
Shut up.
Circuits are like only you.
Oh, we
What?
make weird shapes and bounce them off of each other.
Exactly.
Yeah, but then weird shapes.
What was
there's
it?
only
IRA?
one direction it can go.
Which IRA? The
Yeah,
IRA?
but if it's got like,
No, it's like a
it's got like 16 of
That's
them.
He's not gonna make 16.
No.
That's what you
You're worried.
No, not barely.
I'll do 4.
Oh, 4 is easy. 4?
4 different charges.
He said
Okay.
Are they gonna
Now,
force and acceleration and velocity?
I don't know why he said Irish.
If I've got a
I
positive
mean,
10
yeah,
nanocoulomb
I-
charge
it's
here,
not Irish Republican Army.
and a positive 10 nanocoulomb charge there, and a negative 1 nanocoulomb charge in the middle, will that negative 1 nanocoulomb charge in the middle feel a net force?
No.
Will it feel a force?
Yes.
Feel two of them. Why, Thatch?
It's being pulled in both directions.
Do you have enough information to calculate that?
Yes.
I need-
Yeah.
Of
course.
Because, 9 times 10 to the ninth,
No, we need more information.
newtons meter squared. Ironically,
I need to know.
that's represented by K for Cohen.
Yeah.
So, times 1 times 10 to the ninth to the negative ninth, times 10 times 10 to the negative ninth, divided by 0.02 meters squared. So, somebody run the numbers.
It's K for Conan.
2.25 times 10 to the
So if you,
negative
so like this would just.
It's the only
Times 10 to the
thing
negative
it's got.
fourth.
Uneven,
Yeah.
do you want the front?
Okay?
The force on the outside.
So, in this
Yeah,
situation,
And then
is that gonna, in terms of that negative charge in the middle,
you multiply it by.
is that gonna feel, is the negative charge in the middle gonna feel pulled to the left, the right, both, or pushed?
Either.
Pull
Up or down.
It'll sit there, right?
Yes.
This is receiving the same amount of.
Yeah, but it'll feel pull both.
It'll feel a pull in
Both directions.
both directions,
Yeah.
right?
So it'll
But it's like a tug of war,
Yeah.
so nothing's gonna happen.
Nothing's gonna happen.
Would anything change mathematically if I made that a positive value,
Yeah. Wait, mathematically or?
in terms of the answer? Would it, if that was a positive charge, would we still end up with the same, like, absolute value of the force?
Yes.
Yes.
The absolute value of the force would be the same. But then, what's that going to feel? Instead of being pulled in both directions,
Push.
it's going to get pushed in both directions. Now, what if,
He turned it into a triangle.
I'll get to that. What if I made that one a negative 10 nanocoulombs?
It gains twice the force in the center.
Why, Jacob?
Because it's being pulled one way and being pushed the other way, but both ways it's the same force, so it just doubles.
So, wonderful answer. So if I make that a negative value, okay? So here's what you're gonna have going on. You're going to have it being, if that's a negative and that's positive, it's gonna feel an attractive force this way, but it's gonna feel a push from that one. So the net force that it would feel would be what factor of that?
10 to the negative second. Wait,
What?
4.5 times 10 to the negative 4.
Otherwise known as doubling.
Oh.
That's all I really wanted you to say, was the fact that you would just double it, because it's gonna get pulled and pushed in the same direction. Good with that? Now, this is where we'll get into something even more complicated.
When we get to quantum mechanics.
That's helium. He does.
Are you saying Berg exhales helium?
That's what you exhale. What? Helium.
Did I fill up that balloon? No.
Yes. How do you think it's sticking up there? It's helium.
Charles, you
Mind
realize
blown.
what we're learning? That's literally this is the unit. This is the unit.
I hate helium-filled balloons with every ounce of my being.
It's
Why?
such a
Because helium's
waste.
bad for the environment.
And it's rare.
It's rare, but it's
Helium's
not that rare.
Yeah. It's rare on Earth's atmosphere. In the sun.
just start harvesting the sun?
Yeah, just
I
go,
am
just go
going
mine
to
the sun.
harvest the
Oh,
sun.
yeah.
Have fun.
I'm pretty sure it would be cheaper to try and do that to Jupiter.
No!
That's not even a
Oh.
triangle.
Are you dumb?
Trigonometry.
That looks more like a, look at how he
Let's
makes it
go.
look like a rectangle. He's
Yeah, but
setting
what's
it
the-
up
What's the
for,
distance?
look at it,
Yeah.
look at, I know there's three, dude, look, I know there's
That's so
three
we know the
circles.
measurement.
Yeah,
So
and you
now
get
we have to
$2
do
for
shut
the
up.
so you
Now
start
it's
paying
triangle.
for
Now it's going Look,
Okay,
you're gonna make us, you're gonna make
If I do enough.
oh, I'm gonna make you, yeah. Okay,
Yeah.
I'm gonna make you, yeah.
Yeah.
Okay, so now we're gonna have three charges. Count them, three.
Whoop-de-doo. When
So Q1 has a charge of negative 50 nanocoulombs. Q1 and Q2 are separated by a distance of 10 centimeters.
What's the count?
Q2 has a charge of positive 50 nanocoulombs. Q3 has a charge of positive 30 nanocoulombs. The distance between these charges in Q3 is 5 centimeters. So the first thing I want to figure out is the direction of the magnitude that Q3 feels relative to charge 1.
What?
Good question.
Let's start with this idea.
figure
That's a negative charge, right?
Yes,
True?
yes,
This is a positive charge.
yes.
So what's Q3 going to feel? Push or a pull? It's going to feel pulled in this direction, right? So I need three things to calculate that force. Distance is 1,
and you'd want the repulsion
Charge?
charge, and
against each
charge.
Oh.
Right? I need the two charges and I need
That's
the
the same.
distance. But the distance needs to be from here to here. So now we gotta go old school trig. No, not bad.
I can't do Pythagoras.
So would this not be 5 centimeters? Right? And this would be 5 centimeters. True?
True.
Okay? So, otherwise known as the Pythagorean theorem, I'm going to have 5 squared plus, and then take the square root of that. Square root of 2 times
They're gonna rest.
5. So give me that number in meters.
7.5. Oh, I can't type.
Of course you can't type.
So the distance between those two is going to be what?
So I get to the same.
7.07.
Times
In meters.
in
Oh,
meters.
in meters.
Oh.
Yeah.
True?
Yes.
Okay? Now, this is actually where you can get a little bit clever. So the force is going to equal K. I'm just going to put, I'm not going to write that, I'm not going to write out the Cohen constant. It's just going to be K. Times negative 50 times 10 to the negative 9 times
Big time to squish it.
30 times 10 to the negative 9. Now, if you wanted to, because that's going to get squared, so basically, if you think about it, that was the square root of 2 times 0.05 meters, but that's going to get squared. Oh!
That's good.
So if you wanted to get fancy mathematically, okay, because this is going to be 5 squared plus 5 squared, which is going to be square root of, so square root of 50, which you can write as the square root of 2 times the square root of 25, which you could write as the square root of 2 times 5, right? But then you're going to square it because it's over d squared. So regardless of how you want to think about it, what do you get from the value of that force?
Electricity.
Thank God for calculators. doing this by hand.
2.70 times 10 to the negative 3.
2 point, what?
70.
Huh?
2 point,
No.
what'd you get?
Negative 2.70.
Okay.
Sorry.
Times 10 to the negative
Third.
third. So that's gonna be going in that direction, okay? Now, what's gonna happen to charge 1 and charge 2? What's the only thing that's gonna be different? The direction, because mathematically it's still negative 50, okay? Of the fact that it's positive, right? So now I've got positive 50. I still got a positive 30. The distance is still going to be the same.
Yeah.
So in terms of this, what's going to happen?
It is going to push.
It's going to try and push it this way. True? So that's going to be positive 2.70 times 10 to the negative third.
Therefore,
Now we're even going to go older school.
Yeah.
Older school.
How can we get much older than this?
Vectors.
Oh, could you break that up
I swear we
vectors are more recent.
into X and Y components?
Oh, I'm sure.
Oh, you can do that.
We did do that, but it's old first.
That's old school.
No, but I mean like, wait a second.
Hold on, yes, hold on.
We did vectors before we did.
Now,
I never.
what do you notice about your X components?
Cancel out.
You don't even have to find your X components in this situation because they're just going to cancel each other out. But if you find one Y component, you've also found the second Y component.
The thing stops the signs.
No. Your Y, no.
Yeah,
Your Y components are both going in the same direction.
Yes.
But here's the story. What do you have to have? Because you know what the hypotenuse is. You know the hypotenuse of that is 7.07 times, or the 2.70 times 10 to the negative third.
This is bad.
What do you have to find the X and Y components?
The angle.
The angle.
And
Oh. Boo. Now, so you knew this was 5 centimeters, right? It is actually not bad, and you knew that was 5 centimeters, so what's that angle gonna be? 45. Okay, so it isn't bad, because that's just 45 degrees, so you can do sine and cosine or off to the races. Okay. Last one.
That was not.
And then you get to retire.
You just said racist.
Yeah, you shut up.
I'm not laughing. I'm laughing at him laughing. No, I would never do that.
That's totally false.
I did that yesterday.
Whoa.
And I tried to show it to you. It's on you. Don't worry, there's a second one too.
Really? Oh no.
That's what he called me.
He was?
Only when it was you. I can go, I have a bunch of
I got
Oh, yeah, sure.
You might be like, I don't know what grade.
That's fair.
Okay. He's like 6.
He's definitely not 6. He's way too big.
Okay, so imagine this. You have 2.5 kilogram masses.
Go to jail.
They've both been charged to 10 microcoulombs, or 1 microcoulomb, I'm sorry, 1 microcoulomb.
-6 or something.
And they are 0.25 meters apart, which is about like yay. We're gonna hold them here, and then we're gonna let go of them. And I wanna find the force acting on each one and the acceleration acting on each one.
No.
Okay. The force calculation is easy. What
It's
do you have to
literally
do?
weird gravity.
Force equals your charges over d squared.
Yeah, so that's K.
Charges d squared.
Micro means 10 to the negative 6. So that's 1.0 times 10 to the negative 6 coulombs. Times 1.0 times 10 to the negative 6 coulombs. Divided by 0.250 meters squared. So what do you get out of that?
You forgot.
Square it. Is it the Excel?
You forgot to square.
Which one?
At the denominator.
Charles, wait, did you get
Oh,
the d
you know,
squared?
he's just asking for the force. He's just
This is
asking for the
force.
force.
This is
Yeah,
force.
okay, okay. Yeah,
The bottom one is the acceleration.
You can say it.
No, oh, you're asking? Oh.
Yeah, what's the force?
0.144.
What'd you get?
0.144. Somebody check me.
Okay.
That's what I got wrong before.
No, that seems right.
Yeah, step too far.
Oh,
The
the expert over here. The clown has spoken. Hear him.
You mean the oracle?
No.
The almighty ways.
So, are we good
The
with
village
this?
idiot.
We're good?
Hey, the village
So there's your force. So then,
baby.
is that force
Dog gravy.
going to repel or attract those two masses?
As I said, it's weird
Repel.
gravity.
So the masses are each 0.5 kilograms.
I don't know why this is kind of, it's.
So when you, and this is gonna be important, when you initially let go, what's gonna be the acceleration of each one?
We can talk about it.
0.2.
0.144 divided by a half a kilogram, you get,
288.
is that value of acceleration going to remain constant?
No.
That's initial.
Deacon, you said no,
You're
why?
going to have a jerk.
Imagine this, they're sitting here.
I don't.
I wanna let go of them. They're going to begin to accelerate away from each other.
It's gonna decrease the distance between them. Is gonna-
Ah, there you go.
You have a jerk.
So if you were to draw a
That's the
graph
actual term
of
for it.
acceleration versus distance,
Acceleration, it's very weird.
and here you are at 0.25 meters with an acceleration of 0.288.
Can you flip to the other side?
What's that graph going to do?
Why didn't you ask that? Because he's the one that got it off.
My grade.
Will it ever go to zero?
Because I,
No.
Theoretically, it won't.
It should.
practically it would.
Yeah. That's like, oh no, it will never reach zero.
Yes.
But
We are
doesn't
being
every
influenced by that one thing on the opposite
Okay,
side of the
so your
universe.
assignment for tomorrow is, or Monday, I should say,
It's short.
is kind of a combination of things. So out of the book, you've got 3 questions, 9, 10, and 22. You got problems 8 through 10, 12 through 17, and then you have this problem that I have typed out where you have 2 small plastic beads. I've given you the grams, I've given you the charge. They're 2 centimeters apart. Find the force, the gravitational force, and you gotta go old school. Because I ask you, by what factor is the electric force on the beads greater than the gravitational force on the beads? So to do B, you've gotta go old school. F equals big G M1 M2 over D squared. Okay? So to answer B, you gotta go old school, like old school. Okay? It isn't mass times gravity. God, what was that statement anyway? You gotta go old school, F equals big G M1 2 over D squared. And then you're gonna compare the value of those
That's how you'd have to find
values. And I am done, and you are on your own. So enjoy your 3-day weekend. Thatch,
Should we do that on the paper or on another piece?
you need to just do this like on another sheet of paper, just like put it at the end of the regular book assignment. Yeah, do not answer that problem here, do that on like with your normal other assignments. Okay, for those of you that are gonna help out tonight, they're gonna provide pizza. If you want any drinks, those are on your own. Try to be there no later than 5:15, so I can kind of explain what's gonna happen. We're gonna have some chemistry stuff, we're gonna have some physics stuff. There's 18 of you, so we'll kind of rotate around. I'm gonna do kind of an explanation of stuff at the beginning, and then I'll turn them loose to rotate around, like I'm gonna do like the flame tube with the music.
Oh, yeah.
So, that's always a crowd thing. I just hope I don't. All right, kids, here we go. With this lab from yesterday, hand that in if you have not.
Here, and